So far, we talked about control system. Now, control system, we have something called as the plant. So we have a plant. This plant has some input. It has some output. So you have an input and you have an output. This plant could be expressed as a transfer function. So the plant could be expressed as a transfer function. A plant could be expressed as a state space model. So state space model, or it can be expressed as a differential equation. The idea is you have this mathematical representation of a robot or a quadcopter. And what you are representing is you provide some input and it gives you some output. If output is proportional to input, then the plant is linear. Many a times, output is not aligned with the input. So for an example, if I supply a unit input, my expectation is my output would also be a unit output. But depending upon whatever is the gain of the system, depending upon the inertia of the system, depending upon the damping of the system, the output may not be same as input, which means if you run in open loop, no feedback, you notice that output is different than input. So what it means in terms of robot, you give a command signal for a robot joint to go to 60 degrees. And you would notice you give a command, but the actual angle is not 60 degrees, it's 40 degrees, which means there is some difference, there is some offset. So what we want to do is, we want to run the system in something called as the closed loop. In closed loop, you get the feedback from the output, and typically you have some type of a feedback transfer function. Many a times, the output from the system may be detectable, may not be detectable. So you add some other amplification circuit to amplify the output. But let's assume that the output from the system is detectable, and what you do is you provide this to a summing junction, and in this summing junction you have an input u of t, and then you have a controller over here. So if you look at the way the system is going to flow, is you have a summing junction, you have the positive input, and you have an output which is y of t. And at the end, what you want is you want y of t divided by u of t close to 1. In terms of robot, you supply the signal so that your input is equivalent to 60 degrees of joint motion, which means at the end, the robot should move by 60 degrees. Everyone understood this? But if the robot has inertia, if robot has some damping, or if robot has some dead zone, robot may not respond either quickly, robot may not go to the desired final position, or the robot could overshoot or can actually have some type of steady state error. Everyone understood this? So purpose of this controller C is to modify that error so that appropriate controller signal can be given, and at the end of the day, the output equals input. Everyone understood this? This is the basic strategy that we are doing. Now, I did not talk about a lot more detail in the math, but if you want to study the mathematics of control systems, there is an entire course on linear systems taught in Triple E that will teach you all the basics of control systems. At the end of the day, the idea is this. If you have a plant, you can form something called as a transfer function. So transfer function is nothing but the Laplace transform of output divided by the Laplace transform of input. Now, I want to take a robot case, and this is extremely important problem, okay? Imagine that you have a robot, and this robot is in the form of simple pendulum. Let's make this robot sort of the simple pendulum. So I have a robot that is like, let me see if my, no, it's still not. So the robot is a simple pendulum. So robot is a simple pendulum. Never use this, so. Okay. The robot is a simple pendulum, which is shown something like this. Okay, this robot is given as a simple pendulum. And for the sake of discussion, this has length L, this has mass M, and we have solved the differential equation of motion using Lagrangian approach, Newtonian approach, and Hamiltonian approach. And the differential equation for this robot is given as theta double dot plus G over L sine theta is equal to 0. So the differential equation for this robot is given as theta double dot plus G over L sine theta is equal to 0. Imagine if you have a controller input, u of t, then this equation can be written as u of t. So the equation is going to look like theta double dot plus G over L sine theta is equal to u over t, where theta is my output and u of t is my input. Now, first and foremost, I want to ask you this question. Is this a linear system or a nonlinear system? It's a nonlinear system because sine function is not linear. If you look at the whole sine function is not a straight line. Sine function can be linearized. Sine function can be expressed as a linear function when the theta values are small. Do you agree with me? So I'm going to assume theta is less than equal to 17 degrees because then the linear assumption makes sense. And my equation is going to become theta double dot plus G over L theta is equal to u of t. Now let me make this easier. I'm going to assume L is equal to 9.81 meters. I'm going to assume G is equal to 9.81 meters per second square. So for this pendulum, which has a very long length, this equation is going to become theta double dot plus theta is equal to u of t. Once again, this equation is nonlinear. This equation is linear. Are you with me? Yeah. It depends upon the problem, but what I want to, okay, bear with me for a second. I will answer your question in today's class. But what I want you to understand that since I knew, very important, since I knew for small values of theta, sine theta is equal to theta in radians, that's why I made this substitution. Imagine if we had a double pendulum or a very complicated robot arm. Just by looking at that expression, I will not be able to make these arbitrary substitutions. Everyone understood this? But in this case, since the problem is simple enough, I can write the linear representation of the nonlinear problem. Everyone understood this? Laplace transform, transfer functions only work when the differential equation is linear. There is no Laplace transform that can work on a nonlinear function. What it means, understand, I cannot use Laplace transform when I have sine theta in that expression. Everyone understood this? I cannot find the transfer function of a nonlinear equation. But since I linearize, now I can find out the transfer function. Everyone understood this? So to find transfer function, what I need to do is theta double dot is s square theta of s plus theta of s is equal to u of s. Do you agree with me? And then I take now the differential equation with double dots got converted into an algebraic equation, which means I can collect terms. So I would collect thetas. So this equation becomes s square plus 1 theta s is equal to u of s. Theta s is an output. U of s is an input. So transfer function for this guy is written as theta s, because this is an output, divided by u of s is equal to 1 divided by s square plus 1. Do you agree with me? Now, what I can do is, remember in last class, I talked about PID gains. You add a controller, you can do all that jugglery if you express this plant as 1 divided by s square plus 1, and you can add PID gains and you can do whatever you want to do. Everyone understood this? Now, the question comes is this the only way we can design the controller? The answer to that question is no. Now, so for example, what if I want to start, extremely important. What if I want to start with a nonlinear equation and design the controller? What should I do? So it is also possible. So what I want to do now is I want to write the nonlinear expression, and for nonlinear expression, I want to design the linear PID control. And I want you to understand the assumption here. The original system is nonlinear, but I'm going to use a linear control. Understand, the nonlinear system behaves like a linear system when the output range is very, very small. Which means as long as that nonlinear system output is restricted within this small region, my linear control would work. Everyone understood this? Now, what I want to do is, how do I represent this whole system, and how do I solve this system? So we are gonna work out this problem using MATLAB, but I want you to understand the premise here. Premise here is you have a nonlinear equation, and for a simple problem, you can linearize by looking at the equation. But many a times it is not possible to linearize. In that case, what we do is we use MATLAB to find a numerical linearization. And the beauty of it is, imagine that you have a system something like this. The linearization, the linear approximation is valid near the operating point. Example, if you are here, this linear representation is okay, but this linear representation fails if your operating region or operating point is somewhere else, because you can't fit a straight line and you need to find a new linearization. Everyone understood this? So if you come to robotics 2, here is what's going to happen. The quadcopter dynamics or the fixed wing dynamics is nonlinear. So what we are going to do is we are going to linearize that airframe dynamics at different regions. We are not going to do that by hand. We are going to derive the equation of motion for the aircraft, and we are going to use MATLAB to linearize at different operating regions. For an example, when the aircraft is turning, that's an operating region. When the aircraft is in level flight, when aircraft is taking off, we would find the linearizations in those regions. And we would use PID controls, or we will design the PID controls that are valid in that region. As soon as the aircraft transitions from the first region to the second region, we would change our gains. Everyone understood this? This is something similar to the gain scheduling, but understand, I'm going to show you how to do linearization using MATLAB numerically, because you will use the exact same approach if you want to control your robot. Because your robot control equations, the robot equations are very long. You cannot manually linearize those. You cannot manually design controller. Now, some of you may say that why not to use nonlinear controller? Nonlinear controls are actually very elegant, and sometimes they ensure not only the local stability, but they also ensure the global stability. So, but problem with nonlinear controllers is the equation themselves are nonlinear. Sometimes you get some type of microprocessor computation error. Sometimes the frame rate does not match. So as long as possible, try to use the linear control even for nonlinear plot. And then if the linear control is not working, try to use gain scheduling. If the gain scheduling is not working, then you can go with the feedback linearization or some other elegant backstepping techniques to design the controller. But the strategy would be to start with a linear control, even though the plant is nonlinear. Everyone understood this? One thing I want to write here, because I will show you that when you do numerical approximation, when you solve the problem mathematically using MATLAB, it will give you the same answer. Now understand that I have this differential equation. This is the differential equation. I want to express this differential equation in a state space form, which means what I do is, first, I find out my state space. State space starts with the variable that does not have any dots. So my first variable is going to be theta. My second variable is going to be theta dot. So my first variable is going to be theta. My second variable is going to be theta dot. I'm going to take the derivative on the left hand side, d by dt, d by dt. Now, understand d by dt of theta is theta dot. Do you agree with me? D by dt of theta is theta dot. Nothing great there. But d by dt of theta dot is theta double dot. And the expression for theta double dot is given here, which is minus theta plus u of t. Do you agree with me? So d by dt. Now I have represented second order linear differential equation into two first order differential equations. If you look at the MATLAB script that Euler-Lagrange generates, it does exactly the same thing. It takes second order differential equation or higher order differential equation and writes that as a coupled first order differential equation. Everyone understood this? That is what the Euler-Lagrange does. If you don't understand that, that's okay. But what I want to tell you is, I can rewrite, this is called as the state space. And this expression can be written as theta dot d by dt is equal to, I'm going to write a matrix here, 0, 1, minus 1, 0, theta dot plus 0, 1, u of t. Now what I want you to do is, I want you to look at this matrix equation and tell me that represents the equation that is written on the right hand side. Everyone understood this? So this is called as the state space representation. So this equation is typically written as x dot is equal to ax plus bu. And again, if this doesn't make sense, don't worry about this. We are gonna study this in lot more detail in robotics too. But what I want you to understand is that pendulum, that robot, can be expressed as a differential equation. As the differential equation. That robot can be expressed as the state space formulation x dot is equal to ax plus bu. The same robot can be expressed as a transfer function. So there are three distinct representations of the same system. Everyone understood this? Everyone understood? I said the same representation of the system. Now here is what I'm gonna do. Now the next part, I'm gonna go on to MATLAB. And first, I'm gonna show you how you can design or how you can auto-tune a PID control. I would show you so this is extremely important lesson, so please understand. First, we are going to look at the simple transfer function that we have here. Add a PID control, and tuning PID controls is most of the time trial and error. But there are heuristic rules and there are algorithms that you can use to come up with a good PID controls that's fit with your specification. I'm going to show you how to use MATLAB Auto PID Tuner to tune the PIDs. That would be the first part. So linear plant, linear PID, everything is great. Everyone understood this? In second case, what we are going to do is, we are going to construct the differential equation, nonlinear differential equation, and capture that in a Simulink block. So now you have a nonlinear differential equation, and then we will try to find out a PID gain that would work with that nonlinear differential equation. But in that step, please understand, your original plant is non-linear. You are using a linearization, you are using a linear control. So MATLAB would do something called as the numerical linearization and give you the PID gains. Everyone understood this? I'm gonna show you that. Next thing is simple PID has its own limitations. So there is something called as the 2 degree of freedom PID, which adds weight on the set point and the disturbance rejection. Many a times, simple PID does not work. Rather than going to some complicated method, try 2 degree of freedom PID. This simple weighing technique most of the times would work. So I will show you 2 degree of freedom PID. And last but not least, we are going to start with this original expression and then work that problem out in MATLAB, and we will see if MATLAB can give us the transfer function and the state space representation that we have derived from mathematical techniques. Anyone understood this? Yeah.
Sorry, how could we know which state to linearize?
So when in doubt, bail out. Which means when you do a numerical linearization, basically what we do is we try to find out relationships between all the possible outputs and all the possible inputs, and finally capture the linear relationship. I need to show this to you before I can explain, but let me go through this problem. But this is a very correct problem. So for an example, you have a plant, you have a helicopter, or if you have a quadcopter, there are 8 outputs and 4 inputs. How do you linearize? Then what we do is we select all the outputs, we select all the inputs, and let MATLAB run its numerical algorithm to find the approximate linear relationship between some inputs, some outputs, some inputs, some output, and use those relationships to design the controller. So let me take you through this journey. It's very exciting. So, and this is exactly how you will linearize when you go to industry. Nobody does linearization by hand. Okay, that being said, I'm gonna share my screen and I'm gonna use MATLAB. So I'm on to open Simulink. Bear with me for a second. And I just have this for my reference, but I'm gonna start from the beginning. First and foremost is open a new script. And in this script, what I want to do is I want to go to the library browser. I want to go to the Simulink, and then commonly you can use continuous, and notice there are 2 blocks that I'm going to use. I'm going to use this PID controller block, and I'm going to use 2 degree of freedom PID controller block. So these are the 2 controller schemes that I'm going to use. But before we go further, first, let's add our transfer function. You can do the exact same thing in state space. No problem. You can do PID in state space. That's not a problem. Now, if you remember the transfer function that we had was y of s divided by u of s is equal to 1 divided by s square plus 1. Do you agree with me? This was the transfer function that we had. So what I'm going to do is I'm going to go here, and my denominator coefficients are going to be 1, 0, 1. Click OK. So now I have the same transfer function that we derived for the single robot arm. Everyone okay with this transfer function? Now what I'm going to do is, for this transfer function, first let's see how the response looks like if we have a steady state, if we add maybe a step input. So what I'm going to do is, I'm going to take this step input and I'm going to add this over here. And then I'm going to have sinks and I'm going to add scope. Now understand the goal. The goal here is, if I supply a unit input, I should get a unit output. Do you agree with me? That's my goal. If that goal is not met, which means I don't have a good control. So I'm going to run this. And now you notice that I'll show you something, commonly used blocks to make it more appealing. I would add a multiplexer, and in multiplexer, actually, I will show you both the signals. So delete. I would have this output and I would add this input. So now I'm going to run this, and here observe that my input is the blue line, but my output is that sinusoid. Do you agree with me? That's clearly not how I want, which means if I give my robot an input, go to 60 degrees, rather than robot going to 60 degrees, it's gonna go swinging. That's clearly not the behavior I want. Do you agree with me? Which means I need to add a control. How is it implementing sign? Because basically the poles are purely imaginary. The eigenvalues are purely imaginary. So you give a step input, the response is going to be purely harmonic. So it's like a spring mass system. Anyway, so now what I want to do is, I want to take this guy, copy this, then paste it over here, and then I want to design a controller. So to design a controller, what I'm going to do is, I'm going to move this a little bit to give myself a little bit space. Then what I'm going to do is, I'm going to add a controller block, which is the PID. So I'm going to add a PID block. Connect this PID block over here. Add a summing junction. So this is the summing junction. Please note, the feedback always has to be negative. Feedback cannot be positive. So notice, in summing junction, double click, you have one positive sign. The second sign has to be negative. And what I need to do is, this sum, this guy needs to have a feedback from the output. Do you agree with me? So now look at this. I have a controller. That output of the controller is going to the plant. The plant output is being displayed on the scope. I'm also displaying the input, and clearly right now those PID gains are not properly tuned. So if I run now, you will realize, that I will get some response, but that response may not be, it is different than the open loop. Do you agree with me? But not the way I want. This activity is extremely important. So make sure that everyone has Simulink files or Simulink code in front of you. Now what I'm gonna do is, I'm gonna go to PID. I'm gonna go to PID. And here, if you remember in last class, I gambled. I manually entered some values with a hope that I would get the correct answer at the end. But usually what you do is, you would go down here and then use PID tuner app. And there are different techniques, and you can design PID tuning based on time domain, frequency domain, other stuff. But you click on tune. And once you click on tune, it gives you an interactive way to change or adjust the gains. So I want you to notice that all of a sudden, the PID tuner app would open. Now in this PID tuner app, so what you can do is, what is my final goal? My final goal is my output has to be equal to my input. So now it is showing you reference tracking. There are two things that you need to be very familiar with. One is tracking the reference, and second one is rejecting the disturbance. Tracking the reference means eyes on the goal. So that is the reference that you are tracking. If you want your robot to go to 60 degrees, reference tracking means how close you go to 60 degrees and how quickly. Everyone understood this? The second is disturbance rejection, which means if you go to 60 degrees, if the disturbance rejection is your, so which means, so what is reference tracking? Reference tracking is, I want to finish 2 chapters from robotics 1 today. What is disturbance rejection? Even though my roommates are having a party, I don't get affected. So you have reference tracking and you have disturbance rejection. And most of the times you use both. But this particular case, I'm looking at reference tracking. My reference is my input. It's a unit step input, which means at the end, I should be getting 1. Everyone understood this? Now note, it has automatically tuned the PID gains to track my reference. So can you see that my output is actually 1? There is some overshoot, but this is the output after the PID gains are applied. And these PID gains are automatically calculated here. Can you see? So you will see the PID gains. P is 13, I is 6, N is D is 6, and N is 76. It also gives you additional information about the rise time, settling time, overshoot, peak, gain margin and phase margin. Gives you an information how stable your system is or what is the margin of stability. But you can, so for an example, here is the thing. If I want my response to be faster, then what I can do is I can actually move this over here and check what happens. Can you see that my response time improved? So system responded quickly. If I want my transient behavior to be more robust, I can change this. So there is always some type of a trade-off, which means your rise time. So you will have to make sure that you tune those parameters. At the end, you meet the specs. I want my robot to go to its final position in 0.15 seconds. So my rise time is 0.12. So everyone understood this? Yeah. L is basically the Nyquist frequency that actually changes depending upon how you tune it. So But you can actually look at the important point here is the point I want you to think about is P, I, and D, those gains, they are automatically tuned depending upon your time domain specification. Everyone understood this? If you were to tune the PID in frequency domain, your performance would be measured in terms of bandwidth, in terms of other frequency domain parameters. But at the end of the day, I want you to understand that in this case, the P, I, and Ds are automatically tuned. And then what I'm going to do is, I'm going to go here and I'm going to say update block. And once I update block, notice my PID gains. Now, if I run this, I want you to observe that I have a system. Remember, there are no longer oscillations. My input is tracking quite well based on my specification. No oscillation. Which means if I give a 60 degrees input, then my robot is not going to go haywire. It will go somewhere, there will be an overshoot, but finally it will go to 60 degrees. Everyone understood this? Now, the question is, how do we improve the PID? So this is what is called as 1 degree of freedom PID. In 2 degree of freedom PID, you use a simple trick. You basically add weights on the error and the set points. That gives you a little bit of robust performance. So what's going to happen is now I'm going to show you how would this change if you use a 2 degree of freedom PID. So to use 2 degree of freedom PID, I'm going to copy this block. And then I'm going to paste this block over here. So now I have this block. And now 2 degree of freedom PID, the architecture is slightly different. So in 2 degree of freedom PID, what you do is you take out the summing junction. Oops. In 2 degree of freedom PID, you take out the summing junction. You take the PID block, and then you are going to go to this 2 degree of freedom PID. Can you see this block? 2 degree of freedom PID. Grab this block and place over here. Grab this block and place over here. Now in 2 degree of freedom PID, every PID is going to need a feedback. So what you do is, here you attach your reference on the top. You attach your reference on the top and you add your feedback at the bottom. There is no summing junction. Everyone understood this? In 2 degree of freedom PID, the way it is coded inside MATLAB, you need to supply 2 inputs. One input comes from the reference. Our step input is our reference. And the other input comes from the feedback. So can you see that I have feedback over here? Unlike previous case, you had to find the error and feed that to the PID block. In the previous case, you had to find the error and feed it to the PID block. Here, you don't do that. Everyone understood this? Now, if you double click on 2 degree of freedom PID, I want to show you the difference. If you look at the compensator is another word for the PID controller. Previously, the expression was P multiplied by error, I multiplied by 1 by S multiplied by error, and D multiplied by 1 by S, 1 by S error. Everyone understood this? Now what has changed here? Here you have P that is multiplied with B times R minus Y. So your input is scaled by a number B. Previously it was just R minus Y. But now here it is b times r minus y. So your input is scaled. Your integral term remains the same, but your derivative term, the r value is also scaled by c. So here you have two constants. One constant is b and other constant is c. B is scaling the input which is going into the proportional control, and C is amplifying the input that is going into the derivative control. Everyone understood this? Why is this jugglery? There's a beautiful mathematical explanation for why this is needed. I wouldn't discuss this in this class, but think about it. It's like you are artificially magnifying the effects of input in proportion and derivative term. So essentially what you are doing is you are making the controller gains a little bit more robust. Now, and the change here is what you can do is you can add the set point weight B and you can add the set point weight C, and it can actually change. If your set point weight B and C is equal to 1, it is exactly same as your PID, no change. So if you run the code the way it is, your PID, the PID 2 degree of freedom and regular PID would perform exactly the same. But that is not what we are going to do. We are going to use the PID tuner app to tune the 2 degree of freedom PID. That app will give us coefficient P, coefficient I, coefficient D, and it will also give us set point weight B and set point weight C. Everyone understood this? Now what I'm going to do is I'm going to go to PID tuner app, tune, and again that PID tuner app would open. And now I don't know if you have, I think this plot looks different than the previous plot. You can actually tune this the way you want. You can tune this the way you want. Depending upon your response time specification, depending upon what you want. And then you can see the parameters here. Now it gives you some value of B, it gives you some value of C, and it gave you totally different PIDs. And then update the block. And now, if you see the performance, I need to run this. If you see the performance, you will notice the performance is slightly improved than pure PID. Everyone understood this? So remember this. If the regular vanilla PID doesn't work, then try to use 2 degree of freedom PID before jumping on to any nonlinear techniques. Based on my industrial experience, I can tell you almost 80% of the times, the linear controls, even single PID or 2 degree of freedom PID, would give you reasonably good results. You don't have to go and invent some fuzzy logic or neural network or some complicated controller algorithms. Everyone understood this? Yeah.
For every dynamical system that you try to tune the parameters, you're assuming like the system is going to be under the step function, right? So when we are trying to, for real dynamic system that can go over a range of different inputs, like instead of a unit step function, like still be a ramp function. Is this PID still going to work?
So again, this comes to the fundamental question of how do you design controller for linear time invariant system? I don't know what to do. Now, PID controls, whenever you are designing, the question here is, right now, what is my objective? My objective here is, I want my system to go to the set point. If my set point, if I set point is equal to 60 degrees, I want my system to go to 60 degrees. If I set my set point to 90 degrees, I want my system to go to 90 degrees. The question is whether same PID gain, same control work with a RAM, which means now what you are doing is you are changing the system. And that is an important question. What I want you to do is, it's very easy to check this. Take this out and add the RAM function here. Sources. So what I'm going to do is, I'm going to add RAM function here. And now let's see if this PID control would work. We are trying to control the behavior of the system using a simple linear control. So does that answer your question? Now what happens if you have a sinusoidal input? Please try. Again, it's very easy to try this. Now the next part which I want to discuss, and this is going to take some little bit of discussion, is imagine so far we have a linear plant. We have a linear plant and we have a linear control. Because note, PID is a linear control. So that's all what we are doing. Now what we are going to do is, we are going to use a nonlinear plant. Nonlinear. And nonlinear plant cannot be expressed by transfer function, because transfer functions are only possible because of the Laplace transform. Laplace transform can only be used for linear systems. So if you want to express a nonlinear system, you have to express either as a differential equation or you have to express that in a state space form. Let me start with a differential equation. What is my differential equation? Differential equation is theta double dot plus theta. Okay, let me see. Theta double dot plus sine theta is equal to u of t. Do you agree with me? So here is what I'm going to do. I'm going to write this equation theta double dot is equal to minus sine theta plus u of t. Do you agree with me? Now I'm going to code this expression inside Simulink. How do I code this expression inside Simulink? Now please try to understand. I have this expression. I have two derivatives, which means to find the answer, this whole thing needs to be integrated 2 times. Do you agree with me? Which is what I have, is I have this guy. This guy needs to be integrated 2 times. You can actually construct this equation using Simulink blocks, but I find it easier to construct this using a user-defined function. So I want you to follow what I'm doing. I'm going to user-defined function. I'm grabbing this MATLAB function. Recollect, this is exactly the similar type of MATLAB function that was generated by the Euler-Lagrange. This MATLAB function has an output which is on the left hand side, and it has an input which is on the right hand side. So I'm going to write this y is equal to minus, or I can say sine of u, and I can actually let me just first, before we add controller, let me just add this. So y is equal to sine of u, and then I go back here. So now I have this MATLAB function. This MATLAB function needs to be integrated 2 times. This function needs to be integrated 2 times. So I'm going to go to commonly used blocks, and I'm going to use the integrator here. So one integration is going to give me the velocities. One more integration is going to give me the derivative. And please note that there is this minus sign. So what I'm going to do is I can change this sign here as minus, or I can change the sign. And what I'm going to do is I would feed this output over here. So what has happened? Actually, let me simulate the exact same thing. So I would add a summing junction. Summing junction goes here. This goes here. So what I have is I have this function that is actually I'll make this little bit function of u. Need to make this maybe theta, because that's what I have. And then I'm gonna call this u. I'm gonna call this theta. I'm gonna call this plus u. So now this solves my problem. This is theta here, and then I'm gonna add my input, which is sources step over here. Now please understand what I have here is I have this differential equation. This differential equation looks exactly similar as this. Since this differential equation needs to be integrated twice, I have the first integral, I have the second integral, and I'm going to show you the exact same thing with the mux block. So this is the mux, and I'm going to have this guy fitting here. I'm going to have this input coming over here, and then I'm going to have the scope over here. So now what you can see here is you have a scope, you have the nonlinear differential equation. That nonlinear differential equation gets integrated twice, and we get the result. Now let's see if how does my response look like. And click on here, it will go through the and see the response. Now clearly you notice that the system response is unstable because what I'm doing is I'm giving it a step input, and let me make sure I'm giving a step input and I'm integrating it 2 times, and basically the system response is unstable. Now, how do I add a PID gain or PID control to this system? To add the PID gain, what I can do is I can directly change my controller input. I can directly change my controller input U and add a PID block as a controller. And we will do that in just a second. But what I want you to understand here is this system is nonlinear. And what I want to do is I want to perform something called as the numerical linearization on this nonlinear system to get the approximate linear representation. So here is how you do it. So for that, first we are going to take this out. Then we are going to take this out. And clearly this will also go away. I would add the out over here. So what I'm going to do is this I will take out. And this would be my out. So here. Then I'm going to add in. I'm going to add in. So now what I have is I have the output, which is theta, and I have the input, which is u of t, that are clearly marked. The plant is nonlinear. I want to perform the linearization. So what I do is I go to apps. And when I go to apps, note there is this linearization manager. I click on linearization manager. And once I click on linearization manager, all these sub-functions are visible. So click here, click on the input, and what's going to happen is you will see you can actually assign that input to be maybe an open loop input, or you can assign that input to be something like just input perturbation. So I recommend that you use input perturbation. Then here, this is an output to specify as output perturbation or output. So now you have input and you have output. And then what you do is you basically run model linearizer. And once you linearize the model, what it's going to do is it will numerically do the linearization. And then you can actually click the results, can click the linearization advisor. And we also did that for step. So run this for step. And it will actually do the linearization and give you the linear plant. So wait for it. I'll try to get the charger. It's gonna go through the linearization technique. And it will generate. Now, can you see that this linear plot can you see that this linear plot is same as the state space model that we created? If you want, you can actually convert, look at the transfer function. And can you see that the transfer function that we have is the exact state transfer function that we created. Everyone understood this? Now, what you want to do is you have some output, you have some input. What you want to do is you want to specify what is your output and what is your input. So in this particular case, I will show you once again. This is extremely important. So you have this nonlinear function. This nonlinear function, do you agree with me that u is the input on this differential equation? What is the output of this differential equation? Output of this differential equation is theta. Where am I getting theta? So you have the differential equation that gets integrated once. So now you have theta dot. It gets integrated twice, and now you have theta. So at the end, you are plotting, where we are plotting, that was the value of theta. Everyone understood this? And here is the value of u. So I'm specifying the inputs, I'm specifying the outputs. Then what I did, actually there are different ways of doing this, but for this first iteration, you are assigning the input and you are assigning the output. Input is going in, output is coming out. Can you see these two small arrows here showing input and output? Once that is done, you would go to model linearizer. Once you go to model linearizer, you can linearize with respect to different inputs. Step input is the classic way of linearizing. You click here and then you will notice it will run through the code, and finally it will give you the exact same linearization that we analytically found. If you look at the way, if I were to write down the state space representation of this, it's going to look like theta dot d by dt is equal to 0, 1, then it's going to be -1, 0, theta dot plus 0, 1 mu of t. This is your A matrix. This is your B matrix. So the point what I'm trying to say here is, can you notice the only thing here is it's flipped. Other than that, this is the exact same thing. Can you see that your B matrix is also flipped and your A matrix is also flipped? But at the end of the day, that is what you have. This is extremely important. What does it mean? You have created this great differential equation for your robot. You want to design the controller. So what you do is you program that differential equation inside MATLAB. Believe it or not, when you ran Euler-Lagrange, it already gave you an M function. So what you need to do is you need to identify the inputs in that Euler-Lagrange function. Where are you controlling? Then basically identify the inputs, identify the outputs, and perform the linearization using MATLAB. And once you do the linearization, you can use your PID control to control the plant. Everyone understood this? Yeah.
Why is it for?
Because it's a numerical linearization. And so what they have done is basically they have done something like this. Theta dot theta -1, 1, 0, 0, theta dot theta 1, 0. So answer is not going to change. Only thing is that state representation is different. So this is the velocity, this is the displacement. But at the end of the day, the answer is going to be the same. Last but not least, okay, this is extremely important because when we go to robotics too, we are gonna have these 12 differential equations. We have to design the controller. So we can't linearize those by hand. So we are gonna use the MATLAB to do the batch linearization, which means for each operating point, MATLAB would find out the linear approximation, and we would have a PID control for each operating point, so that for the overall operation duration for all the operating envelope, the system would be stable. And in case if you have controls background, there is the zero pole gain type of representation that also MATLAB can provide. Okay, the story doesn't end here. Now the question is, how do we do all this? All this mathematical jugglery is great. Now, how do we design the controller? And again, to design the controller, I'm gonna go to the PID block. I'm gonna go to the PID block, attach the PID block over here. And please note, it's a single degree of freedom PID. It's a single degree of freedom PID. So I need to add the summing junction. Summing junction adds here. The feedback comes from here. Then I need to add the source step input here. Step input here. This needs to be minus. This needs to be minus. Click OK. And just to be similar to the previous one, actually, I'm gonna add a multiplexer. I'm gonna add a multiplexer. The other multiplexer is gonna go from here. And at the end, I'm gonna have the commonly used blocks. I'm gonna have the scope. Now understand, in this configuration, you have the PID controller, but PID controller is used to control the nonlinear plant. And let's see if it works. Now you go back. So simulation, hit run, click here and see if it works. Clearly it's not working. Now go to PID block, go to auto tune. Now can you see it is linearizing plant? So remember the stuff that we did earlier, this PID tuner is doing automatically. And now update the block. Click OK. Voila. Now you have a linear controller controlling a nonlinear plant. I will stop here.